Okay, good afternoon, students. So, in previous lecture, we have studied about the wall timing diagram. In that, we have seen what is meant by wall timing diagram, and also we have seen the wall timing diagram for four-stroke CI engine. After that, four-stroke SI engine. Okay, overlap. What is overlap? During this overlap, inlet wall as well as exhaust wall remains open. Okay, so that also we have covered in the previous lecture. Also, we have seen the wall timing diagram for two-stroke petrol engine and two-stroke diesel engine. So this is the diagram for two-stroke petrol engine, and this is the diagram for two-stroke diesel engine. Okay. So I hope you have got these wall timing diagrams. So please prepare this very well. This out of these four, any one will be asked in the examination. So today we will see the air standard cycles. So in that, let us see what are the assumptions made in this air standard cycle. The name indicates that in this air standard cycle, the working fluid used is air. Okay, that's why it is called air standard cycle. Now, what are the assumptions that we have made in this cycle? So the perfect gas which is used is a working medium, that is air, which we have to consider as a perfect gas. Next, the transfer of heat that does not affect the temperature of source and sink. Okay. The third assumption, the wall of piston and cylinder perfectly insulated. Okay. That is, there is no heat rejection to the atmosphere, that we have to assume here. Next, the cylinder head is perfect heat conductor or perfect insulator as requirement. The working fluid has a fixed mass. The working medium does not undergo any chemical change throughout the cycle. So this, and one more, the specific heat, that is Cp and Cv, do not vary the temperature. So these are the different assumptions that we have made in the air standard cycle analysis. Now let us see air standard analysis, which is used to perform elementary analysis of IC engine cycles. Simplifications to the real cycle includes. So what again the simplifications of the simplified assumptions that we have made in the air standard cycle analysis are: first is fixed amount of air for working fluid. Okay, that is ideal gas. Compression process not considered. Intake and exhaust processes are not considered here. Engine friction and heat losses not considered. Okay, and specific heats independent of temperature. These are the different simplified assumptions that we have made in the air standard cycle analysis. Okay, next let us see the different cycles that are used in the air standard cycle analysis. That is, first is CARNOT cycle, second is OTTO cycle, third is diesel cycle, DUEL cycle, and next is Brayton cycle. So let us see first what is in the CARNOT cycle. So everybody knows what is this CARNOT cycle. So here if you see this case, you see here, just one second, I'll show you. So this point 1, 2 indicates the isothermal expansion process. 2 to 3 process is the isentropic expansion process. 3 to 4 is isothermal compression process, and 4 to 1 is isentropic compression process. Okay, so these are the 4 processes that are involved in the Carnot cycle. So this is the pressure volume diagram, and this is the temperature entropy diagram, that is TH diagram. So here if you see, during 1 to 2 process temperature remains constant, and during 3 to 4 process temperature remains constant. So this 1 to 2 and 3 to 4 processes are called isothermal processes, that is constant temperature processes. Okay, so I hope you understand this different processes that are involved in the Carnot cycle. And if you want to calculate the efficiency of this Carnot cycle, then here by this formula, that is efficiency of Carnot cycle is equal to 1 minus TH upon TC. What is TH here? That is the higher temperature at which the air is come inside the engine or that particular system. Okay, and TC is the lower temperature, is atmospheric temperature, I can say that. So TH is higher temperature and TC is the lower temperature. Okay, now let us see next. So this TH is source temperature and TC is sink temperature. Okay, now let us see the OTTO cycle. So basically this OTTO cycle is used for a petrol engine. So if you want to calculate the performance of the petrol engine, then definitely we have to use the Otto cycle. Okay. So remember, this is for petrol engine. Okay. So here, what are the different processes in the Otto cycle? Here you can see 1 to 2 is isentropic, sorry, adiabatic reversible processes. These are the reversible adiabatic processes. Okay. So here 1 to 2 is the suction. Okay. Sorry, compression. 5 to 1 is the suction process. At a constant or the little bit lower pressure, the suction takes place, and from 1 to 2 the compression takes place. Okay, so this is the 1 to 2 is the compression process, adiabatic compression process, we can say that. 2 to 3 is constant volume heat addition process, because the sparking takes place during this particular process, that is 2 to 3, and heat is added into the system in the combustion chamber with the help of spark plug. 3 to 4 is the expansion process, where pressure suddenly reduces to the pressure number 4, okay, at point number 4. And 4 to 1 is the exhaust process, during which heat is rejected to the surrounding. So just we have to remember, in this Otto cycle there are two constant volume processes and two adiabatic or isentropic compression. One is isentropic compression and one is isentropic expansion process or adiabatic process. Okay. Now let us see this diagram on the TS diagram. So this is the TS diagram, okay, temperature entropy diagram. So during this, what will happen? So as we have already mentioned that during the process 1 to 2, entropy remains constant. So that's why this 1 to 2 process is also called as isentropic compression, and 3 to 4 is also called as isentropic expansion. Okay. And here from 2 to 3, actually a lot of heat is added into the combustion chamber. That's why the temperature suddenly rises to from point 2 to point 3. Okay. And 4 to 1 is the expansion process. Okay. Now let us see how to calculate the efficiency of this particular Otto cycle. So just I have mentioned this. The air standard Otto cycle is an ideal cycle that approximates a spark ignition in internal combustion engine. It assumes that the heat addition occurs instantaneously while the piston is at top dead center. Okay. And by using this formula, okay, by using this formula we can calculate the value of efficiency the Otto cycle. With this 1 minus 1 upon R raised to K minus 1. What is R? R is the compression ratio. R is compression ratio, and K is the adiabatic, that is polytropic index. Okay. So you know that. So for air it is taken as 1.4. Okay. Where R is compression ratio, right? Now let us see the diesel cycle. So what happens in the diesel cycle? So if you see here in this case, what is there? Here constant pressure heat is added into the combustion chamber. This is the only difference between Otto cycle and diesel cycle. So here there is one constant volume process and there is one constant pressure process, and two isentropic processes are already there. Okay, so that is the only difference here in this case, okay, as compared to Otto cycle. Let us see this diagram on TS diagram. So here you can see two isentropic processes, that is from A to B and C to D. There are the two isentropic processes where there is no heat rejection or gain system. But during during B to C, the heat addition takes place, and during D to A, heat rejection takes place. Okay. This is the air standard cycle, which is used to be compression ignition internal combustion engines, and heat is added at the constant pressure in this case. It is the value formula to calculate the value of efficiency. So this is the formula by using which we can calculate the value of efficiency, thermal efficiency. 1 minus 1 upon gamma to R raised to gamma minus 1, 4 raised to gamma minus 1 upon minus 1. So here these are the notations there. Here R is the compression ratio and O is cutoff ratio. So in this case, what is the value of cutoff ratio here? Is RC is equal to V3 upon V2. V3 upon V2 is the cutoff ratio, and compression ratio is V1 upon V2, and expansion ratio RE is given by V4 upon V3, and this is the value of gamma, that is 1.4. Cutoff ratio into expansion ratio must be equal to compression ratio. This is the formula that you have to remember. Now let us see the dual cycle. So dual cycle actually is the combination of diesel cycle and Otto cycle. So if you see here, at this particular point, if you see here, heat is added at constant pressure, and here heat is added at constant volume. So this is the combination of this particular Otto cycle and diesel cycle. When we consider heat addition at a constant volume, then it is a Otto cycle, and when we consider heat addition at constant temperature, at constant pressure, then it is a diesel cycle. Okay? And these are the two processes which are common: adiabatic or isentropic compression and isentropic expansion, and 5 to 1 is the exhaust process. Okay, so let us see this on TS diagram. So this is the TS diagram. Here you can clearly see how it looks like. So here, okay, at 2 to 3 heat is added at constant volume, and 2 to 3 to 4 heat is added at constant pressure. Isochoric means constant volume, isobaric means constant pressure. Okay, other things are same. So 1 to 2 is isentropic compression, that we have already discussed. Next, let us see what is this dual cycle, where it is used. The dual combustion cycle, also known as a mixed cycle, Trinkler cycle, Silliger cycle, Sabate cycle, okay, is a thermal cycle, that is a combination of Otto and diesel cycle, as already we have discussed. This cycle is mainly used in diesel hot spot ignition engines. And how to calculate the efficiency? So by using this formula, we can calculate the value of here efficiency. Okay, right? Just wait. So this diesel cycle we already studied. This is the dual cycle. Okay, and this is the formula: 1 minus 1 upon R raised to gamma minus 1 in bracket RP, that is pressure ratio, RC compression ratio raised to minus 1 gamma minus 1 upon RP minus 1 plus gamma into RP RC minus 1. Okay, now let us see the difference between this particular Otto, diesel and dual cycle. So this also question may ask in the examination. So let us consider for same inlet conditions. Okay, if you consider for same inlet conditions, that is P1 V1, and same compression ratio, that is P2 upon P1. Okay, so if you see this cycle here, in this case, that is on the pressure and volume and TS and entropy, that is temperature and entropy diagram, then you can see here the efficiency of diesel cycle, okay, is much more higher than the efficiency of the Otto cycle. This is the Otto cycle. Sorry, this is the constant volume process, and this is the constant. This is the constant pressure. That's why it is a diesel cycle. Okay, this one is the diesel cycle, and this, if you consider this one, this is the Otto cycle. So therefore, here in this case, for the same inlet conditions, that is pressure, volume, and same compression ratio, we can say that efficiency of Otto cycle is more than dual than diesel cycle. And for the same inlet conditions of P1 V1 and the same peak pressure, so but if you consider for the same peak pressure, then we can say that here, if you see, for the same peak pressure, we can say that the efficiency of the diesel cycle is more than efficiency of the dual cycle, which is greater than efficiency of Otto cycle. So for same compression ratio, diesel efficiency of Otto cycle is more, and for same peak pressure, efficiency of diesel cycle is more. Okay, so remember these points. Next, let us see the Breton cycle here.